All right, believe it or not, the last lecture in gases and gas laws for this unit is gas stoichiometry. If you've made it to this point and have done all the homework, you're right on pace. After this lecture and doing the homework assignment, I will put the answer key online. It's not part of the other answer key, but there'll be a separate one with the homework that follows this page. Once you have completed that, that's really all I'd like you to have done up through the end of this week. And then next week being spring break, technically it was our spring break, so in essence you kind of have the week off there. I might put a couple things online, just some fun interactive type of things. But once Ms. Fassler and I meet tomorrow, we'll get a plan moving forward as to what we're planning on doing when we come back if we don't reconvene after spring break, what our plan will be moving forward and what we're going to send out to you guys through these online resources. So today's objective is on gas stoichiometry, and just like the name implies, again we're going to use stoichiometry, factor label method, to make some of these conversions. Okay, so let me make this a little bigger. All right, so like typical stoichiometry, we are going to be given an amount of one substance and figure out the amount of something else. Now with gases, probably the easiest measurement that we can make on it. Excuse me, my pen wasn't up and working. The easiest measurement that we can make on a gas is its volume. It's something that we can easily collect and easily measure, much more so than even mass of a gas. So with volume of a gas, something that we're going to measure. And what we can find out with gas laws is that when we have a reaction, that those coefficients out in front, what do they mean? Well, 1A producing 2B means 1 mole of A reacted or consumed will produce 2 moles of B. If both of these substances are gases, because if we treat them all as ideal gases, which we will for this unit, it doesn't matter what the gas identity is, A can be the same as B because we treat them both as ideal. Therefore, 1 mole and 2 moles of gas means that the volume of the gas will be 22.4 liters of A will produce 44.8 liters of B. Or 1 liter of A will produce 2 liters of B. So we can treat the coefficients just like a mole ratio, a mole to mole problem. We get down to B when we do a volume to volume problem. This is literally a one-step stoichiometry problem where all we've got to do is use the coefficients. If both of the substances are gases, 1 mole of A producing 2 moles of B will be the same as 1 liter of A producing 2 liters of B. In 1 liter of A, the number of particles compared to 1 liter of B, the number of particles in essence are the same because they're both ideal gases. All right, that's probably the most difficult concept in this unit. The rest of it is mostly just using mathematics. All right, so the first problem, you got to be able, in any stoichiometry problem, we've got to be able to get the coefficient. So we've got to balance the equation. So hydrogen gas reacts with nitrogen gas at constant temperature, pressure, produces ammonia. If you want to pause the lecture now and try to do it on your own, please do, but I'm going to move forward here. So nitrogen gas reacting with hydrogen gas. I'm not going to put the states of matter since they're all gases. Ammonia, that's one thing that on a typical test or quiz question, I would give you the formula of it. Ammonia is an organic name. So that's NH3. Oops. So to balance it, we need 3 in front of the hydrogen and 2 in front of the ammonia. Again, what do those coefficients mean? We just kind of talked about it. The coefficients either imply the mole ratio, the molecule ratio at the lowest level, and for gases, it can also apply the volume ratios. Okay, so let's go ahead and do our first volume to volume problem. What volume of oxygen gas is needed to completely combust 4 liters of propane gas? Okay, so it's a combustion reaction. Propane is C3H8. It is a gas. Combustion reactions mean we got to have oxygen. The nice thing about combustion reactions is we get carbon dioxide and water. And we'll assume that they're all gases. Even water, because combustion is at such a high temperature, usually water is going to be in the gaseous state. 3 carbons, so we need 3 carbon dioxides, 8 hydrogens, we need 4 waters, 3 times 2 is 6. 4 times 1 is 4. That's 10 oxygens. We need 5 oxygens. Now the reaction is balanced. All right, so doing this problem, if I have 4 liters of propane, a liter to liter problem, a volume to volume problem, literally is a one-step problem. All we need are the coefficients. So the propane will go on the bottom. We're trying to figure out the oxygen on top. 5 liters to 1 liter. For every 1 liter of propane gas, we need 5 times as much oxygen to react with it. So we get the answer of 20 liters. Okay. Next problem. How many liters of carbon dioxide are formed when 4 liters of methane reacts with oxygen? So again, it's a combustion reaction. These are all gases again, so I won't write down the states of matter. Balancing the reaction, we get 2 water and 2 oxygens. Now in this problem, it's slightly different because they've given us the volume of methane and they've given us the volume of oxygen. And they're asking for the volume of carbon dioxide. Last unit, or actually 2 units ago when we did stoichiometry, when we are given amounts of both reactants, what type of problem is this? It's a limiting reactant problem. So the question becomes, when we did those problems, what did we do to solve those problems? Well, we end up doing the math for both of them independently of each other. So if I have 4 liters of methane, how many liters of carbon dioxide will we produce from that? So again, a volume to volume problem is simply using the coefficients. And we see that both of them have 1. So 1 liter of methane will produce 1 liter of carbon dioxide. So if the methane was the limiting reactant, we would produce 4 liters of carbon dioxide. All right, let's look at the other reactant, because one of these reactants is going to run out before the other one is. For every 2 liters of oxygen, we'll produce 1 liter of carbon dioxide. Doing the math here, 0.25 liters of carbon dioxide. We can see that the answer, as always, is the smaller of the two. So the amount of carbon dioxide can only be 0.25 liters, or 1/4 of a liter of carbon dioxide. We can't produce the 4 liters because it would run out, because the oxygen would be totally consumed once 0.25 liters of carbon dioxide is produced. Okay? All right, lastly, we might end up doing a volume to mass stoichiometry problem. Okay? All right, so we look at problem 1 here. Ammonia is synthesized from hydrogen and nitrogen gas. Okay, so again, we're going to use this reaction up here to do problem 1. So I've already got the balanced equation. I have 5 liters of nitrogen at 3 atmospheres and 298 K. I want to figure out how many grams of ammonia. So I know the volume, the pressure, and the temperature of the nitrogen gas, but I want to figure out the mass of ammonia, a different substance. So I know the amount, the volume of one substance. I want to figure out the amount, the mass of something else. This is stoichiometry. So the first thing I need is the balanced equation, which I have up above from problem 1a. Okay, so now the question becomes, how do I do a problem like this? Well, first of all, the first key question to ask is, are we at STP? And looking at the values, we can see, no, we're not. 3 atmospheres is not standard pressure. Therefore, if we're not at STP, we cannot use molar volume or the conversion factor, 22.4 liters per mole. If we are at STP, we can use that as a conversion factor of volume to moles, much like we can use molar mass to convert mass to moles. We can't use this problem because we're at STP. What else allows us to convert volume and pressure and temperature into moles? And again, moles is given by letter N. If I've got P and T and V and N, what equation allows me to do that? Ideal gas law. The ideal gas law is going to allow me to convert the volume of the gas into the moles of gas. So if I rearrange this equation and solve it for n, if I move the r and t over, if I divide it out, the pressure times the volume divided by the gas constant and the temperature is going to give me the moles of the nitrogen. Once I know the moles of the nitrogen, I can then do a mole to mass problem that we learned back about a month ago. All right, plugging in my numbers. The pressure is 3 atmospheres, 5 liters. In the ideal gas law, the volume must be in liters. The R, again, make sure to match it up. We're going to use the R that is 4 atmospheres. 0.0821 is what we use for atmosphere problems. And 298 Kelvin. The temperature must always be in Kelvin. Okay, going and punching in the calculator, you should end up with a value of 0.613 moles of nitrogen. Now we can treat this just like we did a couple units ago. And hopefully you haven't forgotten how to do a mole to mass problem. The first step in a mole to mass problem, since we already know moles, is the mole ratios. Whatever is on top becomes a unit on the bottom. Okay. For every 1 mole of nitrogen, there are 2 moles of ammonia produced. Then we multiply by the molar mass. The molar mass of ammonia is the mass of 1 mole. Adding up all the elements, we get a molar mass of 17.04 grams. And doing the math, we get our answer of 20.9 grams of ammonia. So whenever we have a problem that is not at STP, we have to use the ideal gas law to convert volume to moles or moles to volume. Okay, so you must use that gas law. Okay, all right, let's look at problem number 2. How many grams of calcium carbonate need to decompose to produce carbon dioxide gas at STP? All right, calcium carbonate, CaCO3, is a solid. It's not a gas. It's an ionic compound. Calcium carbonate decomposes into calcium oxide, another ionic compound. It's a solid, and carbon dioxide gas. The biggest problem that students do is they plug solids into gas laws. You can never, ever, ever do that. You can only plug volumes and pressures and temperatures of gases into gas laws. You cannot use solids. Okay, so in this problem, the only gas is the carbon dioxide. Decimeters cubed, cross it off. Again, I'll never have that on a quiz or test for you guys. 9 cubic decimeters is the same as 9 liters. So I have 9 liters of carbon dioxide. We are at STP, so that's very beneficial. If we are at STP, we can use the conversion factor of 22.4 liters per mole, just like molar mass or Avogadro's number of particles per mole. So the first thing we can convert volume to is moles. Doesn't matter what the gas is. Could be carbon dioxide, oxygen, methane, whatever it is. Every gas is the same if we treat them as ideal. So 1 mole of any gas occupies 22.4 liters. So 9 liters is less than 22.4, which tells me it's less than 1 mole of that gas. Liters cancel. We're trying to go to grams of the solid. So now we can do moles of carbon dioxide to moles of calcium carbonate. This is what makes it stoichiometry. Whenever we have a mole ratio, that's a stoichiometry problem. This is a 1-to-1. And lastly, the molar mass will allow me to convert the moles of calcium carbonate into grams. 100.09 is the molar mass of calcium carbonate. All my units cancel, and I'm left with grams of calcium carbonate. Going ahead and doing the math, we end up getting the value of 40.2 grams. All right, last problem. How many liters of hydrogen gas can be prepared from 0.2 grams magnesium reacts with hydrochloric acid, STP? Again, we're at STP, so we can use the molar volume. So this is much like problem 2, but now we're going from the mass of the solid to the volume of the gas. So this literally is problem 2, but now done backwards. All right, the first thing we need is the reaction. Magnesium reacts with hydrochloric acid. Hydrochloric acid is HCl. We get magnesium chloride and hydrogen gas. The only gas in this problem, again, is the hydrogen. Everything else is either an aqueous solution or a solid. Coefficient of 2 in front of the HCl, and we should have the reaction balanced. So now we have 0.2 grams of magnesium. Since it's a solid, we can convert mass to moles using molar mass. Next step always is the mole ratio. And we're going to hydrogen. 1:1. And lastly, we don't want to know the mass of the hydrogen, we want to know the volume of hydrogen. And again, if we are at STP, we can use the ideal gas law. Now, what happens if we're not at STP? Well, then we would have to stop here and calculate the moles of the hydrogen and then plug that number in for N up into the ideal gas law and solve now for the volume if we are not at STP. So this would be like doing problem 1 backwards. So even if you stopped here and plugged in the ideal gas law, you would get the same number if you were to use 22.4. So it really doesn't matter how you do the problem, but understand if we're at STP, we can use 22.4. We cannot use 22.4 if the pressure and temperature conditions does not match STP conditions. Going ahead and doing the math, we get 0.184 liters of hydrogen. So there are some examples of how to do stoichiometry problems of mass to volume or volume to mass problems. Make sure you can do both these problems forward and backwards. As I've said, if it's a volume to volume problem between two gases, we can just use the coefficients. And that's pretty much it for gas stoichiometry. So all of the mass of this unit is either plug and chug into a specific equation or to use the ideal gas law or 22.4 whenever we're doing these stoichiometry problems. Hopefully it makes sense. If not, shoot me an email. I can show the problems, or if we need to do a video chat online, or if we can go ahead and do that. But otherwise, hopefully, get through all of your homework, take a look at it, and as I said, later in the week I'll send out a Canvas announcement talking about how we plan on moving forward in the upcoming weeks. Otherwise, have a great night and stay safe. All right, talk to you later.